Hello and good day. I heard of the popular formula 8 inches per mile squared, and I decided to prove it or disprove it, whichever one, right? So imagine this is the Earth, right? And you have 2 points, point A and point B. You have a distance between them along the surface of the Earth. That is a distance d, and then you have the radius of the Earth that goes from the surface of this point B to the center, and then this from the center to point A as well, right? And then because of the curvature drop in moving from point A to point B, you have this value y here, right? Because of this curvature drop, right? So the y represents the curvature drop as a result of this distance d moved, right? So therefore you have this to be the radius of the Earth, you have this to also be the radius of the Earth, and you have this from the center up until this point here will be the radius minus y, or r minus y, and then the rest will just be y up until point A. Good. Now basically the way we would go about proving this 8 inches per mile squared is first by proving a formula, right? A proper formula, right, that is not approximate. It's not an approximation, it's an exact formula, right? After doing that, we can then proceed to get the approximations, the 8 inches per mile square approximation. Yeah, so I think with that we can begin. Now the way we will go about trying to prove the formula is that we will try to find a direct relationship between y, which is the curvature drop, and the distance moved away from the starting point of point A, right, which is d. So we are trying to find the relationship between y and d essentially. Moving on. So you can read through the entire solution and all the points I make, right? This solution is linked to the description box of this video. Now for the for proving the exact formula, let's consider the first right angle triangle, right? So if in case you didn't see this right angle triangle in the previous diagram, here it is, right? The right angle triangle. Good. Now we use the SOHCAHTOA formula, which is the adjacent divided by hypotenuse equals cosine theta, right? So you have theta here, and this is r minus y, and then divided by the hypotenuse, right, which is the radius. So you have this equation here, and then you just simplify this, and once you're done simplifying it, you should have this formula right here. Good. Now that you have this formula right here, you can go through the steps to confirm that this is exactly what you get. Now that you have this formula here, you can move on. Now we apply the formula to find the length of an arc. So there is a standard formula for finding the length of an arc, and in this case the arc that we're looking at is simply the distance d between point A and point B that we're trying to find, right? So we use the arc length formula. So the arc length formula that we would use here is d equals r theta, right, where theta is in radian, right? Now we can make theta the subject of the formula for this equation here, because we don't really want to be working with angles, right, when we are trying to calculate our curvature drop. And at the same time, we also want our curvature drop to be in terms of the a distance covered, right? The distance along the surface of the earth covered, so that we can have the relationship I spoke about at the beginning, which is a relationship between y and d. Perfect. So this is the formula. This is the exact formula that would help us calculate at any point in time the curvature drop given the distance away from the observer, right? Or given distance away from a particular point on the earth. Good. Now we can proceed to do the approximation now, right? Now, to do the approximation, we will use the Taylor series expansion of the cosine function, right? So we know the Taylor series of the cosine function is this, right? So we'll replace x with d divided by r, because that is what is in our formula, right? And then we will have this expression here. Now, before we apply our approximation, right, because this goes till infinity, right, so it's still not yet an approximation. So before we apply the approximation, right, we need to also understand a few things, right? So I took the liberty of finding like longest captured distance, right, and it's 275 miles according to this article here, right? So now, and we also know that the radius of the earth is 3,963 miles. So therefore, this ratio of d divided by r, we can estimate what each term of this cosine function will be, right? So that we can know which terms are significant or play a significant role in defining the value this cosine function ends up becoming, right? So we are trying to just find which of these terms, right, plays a big role in determining which what the final value of cos d over r will be, right? So now and note that by using 275, which is the longest distance ever recorded, it implies that we cannot go beyond this. So this is the maximum, right? I'm taking this as my maximum, right? Let me put it that way. I'm taking this as my maximum, right? Useful distance, basically, right? So if you say 275 divided by 3,963, we have this, and you square it, you have this. If you take the fourth power, you have this, right? So you can see that when you square it, and when you take the fourth power, the squaring or the quadratic expression is 1,000 times more relevant than the quartic power, right? So this just simply implies that we should probably just truncate this expression after the quadratic power right here, right? But to further elucidate this point, right, since we're gonna be trying to calculate the curvature drop in inches, and 3,360 inches make 1 mile, it makes sense for us to multiply these indices here by 63,360, right, and then see the type of values or the kind of inches we should be getting, right? So when we do it for the first value, for the quadratic value, we get 305 inches, which is pretty significant, right? We can notice that kind of curvature drop. But if you look at for the quartic, you have 1.5 inches, which is very difficult to observe, right? A drop of 1.5 inches. Okay, good. So now that we have basically established that, okay, we do not really need the quartic and above expressions, right? So we can truncate our cosine, right? We can truncate it at the quadratic level. So we can then simplify it. Once you've simplified this, you have this. Now you can substitute this this expression here into your step 5, right? So the step 5 where we left off right here, we'll just come and substitute it right here. And then yeah, so when you substitute that, you have it here, and then you can then break it down. Once you're done breaking it down, you would have this expression. Again, this is another expression that we can use. This has no cosine in it, right? All you just need here is the distance you require, right? The distance you're trying to look to observe, right, along the earth, and all you just need is the radius of the earth, right? So this formula is way better, but we want to make it even simpler, right? We are trying to approach 8 inches per mile squared, or we are trying to see if that is true or not, right? So say currently y is in miles, and we would like it in inches, right? Because y is currently in miles. If you do the units cancellation, right? So now to turn it into inches, we just multiply by 63,360 inches divided by 1 mile, right? And after the units cancel, we have this expression here. But at the same time, it's also important to note that d and r are still in miles. So since they're still in miles, we can then take the r value. Obviously, we know r is radius, and radius is 3,963 miles, right? So we can just plug that into the formula and then do some cancellation, and then we have y equals, or y is approximately equals to d squared times 7.994 basically, and this basically approximates to 8. So therefore we have y to be approximately equal to 8 and d squared times 8, all in inches, right? While where d is in miles. Good. So now we have the popular approximation of 8 inches per mile squared, which is interesting, right? And yeah, there is one implication of this, right, that I was able to think of, right, which is that the formula itself is accurate to within around 2 inches, right, for a distance of around 300 miles. So that is if you're, let me scroll back to the top. So that is if your d here is 300 miles, then your curvature drop that you calculate using the formula will be accurate to within 2 inches. And I think that's pretty good, right? That's a pretty good approximation, right? And how did I reach this conclusion? It was because of this calculation that we did here. Right? Okay. So with that said, that is the simple proof for the 8 inches per mile squared. I hope I didn't go too fast, and it makes a lot of sense. If you feel I didn't make sense at any point, please let me know. Okay, no problem. Thank you so much for watching. Enjoy the rest of your day.